Excellent. Okay, well, thank you for inviting me to this workshop. It's been really good so far, and I look forward to continuing our work with y'all. So I'm Seth Johnson from the Oak Ridge National Laboratory in the HPC Methods and Applications, Nuclear Applications Group. And I am the code lead for Celeritas. Tom Evans is the PI, and we work with a number of other very valuable people at Fermilab with Philippe and Sun and Guillerme and other people at Oak Ridge, Stefano, our postdoc, Amanda at Argonne, and Vince Pascuzzi at Lawrence Berkeley. And so I'm going to go over some of the work that we've done in our sort of startup GPU-based particle transport application. So the objective is basically get a on-device HEP particle transport code so that we can meet the simulation requirements for the high luminosity upgrade for LHC. So the other presenters have done a really good job today of showing the driver for the increased compute performance requirements. So I'll leave that to them. We think that, as Andre said, this is a great time to be focusing on GPUs. The technology's really matured. There's been a lot of previous efforts that have dipped their toes into GPU Monte Carlo applications, as well as GPU high energy physics. So we've got some experience built up, even though nothing has really met maturity yet in the software area. And our connection at Oak Ridge through the Exascale Computing Project, ECP, gives us a lot of valuable personnel connections, as well as experience in the or at least the Monte Carlo particle transport physics on GPUs. So we think we're well positioned to drive this startup application. So one of the questions that we often have had so far is the long-term strategy for integration of the JANT4. And there's a number of possibilities that we're looking into. We're still in the very early stages, so we haven't spent too much worrying about it. But one possibility that Sun is looking into, for example, is using the new task model in JANT4 to offload some of the EM physics work to Celeritas so that we could run some of the showers on the GPU while JANT4 handles the hadronics and other stuff. Another, possible end game for this is that Celeritas becomes a part of the broader LHC workflow, either as a fast simulation or possibly even as a high fidelity if we end up meeting our goals and getting the requisite physics. And obviously some combination of both of these is quite possible too. So our real goals are, we want to be able to use the heterogeneous architectures that are present on modern day laptops, as well as most of the high-end compute centers that are being stood up. There's been a lot of talk of investment into GPUs for high energy physics community as well. We want to be able to integrate with the existing workflows that are in place for detector modelers and experimentalists. So that includes using the JANT4 geometry models with GDML and reading the high HEP MC3 formats and so forth. And of course, being able to use the actual requisite physics for high energy physics simulation. So our preliminary focus is on electromagnetic physics. So that's, I think our first year goal is trying to get the standard physics that are in JANT4 working on device. And again, we're trying to target the most compute intensive component, which is the detector modeling and hit generation. So we've already been, really kind of wowed with how collaborative this community is. This is our first project where we've gotten the chance to work extensively with Fermilab and CERN and so forth. So as Andre mentioned, we're working with them on some of the VekGeom and startup stuff for Adept. We've got support through DOE and the Oak Ridge computing facilities and the xScale computing projects. There's 4 main US DOE labs working as part of Celeritas, and we want to make sure that as we go along, we're collaborating with the actual detector modelers and so forth so that we can meet and adapt to their requirements. Okay, a little bit about the code base. So right now we've got about 11,000 lines of code itself, and that doesn't include 7,000 lines of comments, 5,000 lines of tests, and so forth. We're taking a bottom-up development approach, kind of like what Adept is doing. With I like the Fisher-Price model that Andre said, where we want to have a large kind of placeholder structure in place, but focus on individual small components that we can progressively build up together. And by focusing on such components at a small level, we'll be able to reorganize them to restructure them for optimal performance on the GPU. The integration aspect of pulling these tiny bits together is guided by our group meetings that we have multiple times a week, and a progression of mini apps so that we can do performance evaluation and guide the glue pieces effectively as time goes on. 3 main focus areas that we've got developing. So the framework that we have, we've got a GitHub wiki that you can look at if you're interested in kind of seeing what some of the guiding principles are, or I can ask in the questions. We're going to be using the Shift Monte Carlo code that we've developed at Oak Ridge, which is a neutron transport application for reactor physics applications, and so that's been successfully tested at scale on the Oak Ridge computers to simulate real life applications with I think roughly a factor of 20 speed up from the full many core CPUs that are on the device. So we've have experience with getting Monte Carlo GPUs running performantly in a production manner. For physics, we're going to be leaning heavily on Jant for cribbing, in a lot of ways, but we think that that's the most reliable way of starting off, is by using Jant, both the physics implementation and where we can using Jant for to sort of process the data, which we then adapt for performance on the device and run with our own GPU code. And then for geometry, we're going to be relying on VekGeom, which has the ability to import these GDML detector definitions and run them on GPU. So one of the key abstractions that we have in place is being able to separate the memory management and memory layout from the actual compute code. So there's a lot of encapsulation that from a developer perspective ends up being pretty easy to work with. And what this lets us do is develop and test the code on the CPU, but run the actual physics on the GPU. And we do this by basically having a separate data container that stores the particle data and so forth, the material data. And then we instantiate another view to that data that takes the local GPU thread ID. And that view is what actually allows us to do all the computational work. And so this should allow us with a pretty robust protection from changes to different programming languages over the years. So if we have to switch to HIP, or if we want to use Cocos to give us performance portability, this mechanism will give us a pretty easy way of doing that. So our first mini app was basically demonstrating our hookups into VekGeom. So here's a ray trace of the CMS detector model and GDML. So this is a slice along the z-axis where each horizontal line is a separate GPU thread, and they're all running in parallel. For this version, the VekGeom library requires the tracks to actually be initialized on the host and copied to the device. So we're not yet at full on-device ray tracing capability, but we're getting there, and we should, with Andre's help, be there soon. Our second mini app is sort of the more interesting one. So we ported the KleinAshina model, the Compton without electron binding, to the device, and we ran a simple mini app code where we could do a actual physics comparison against JANT4 for some of the preliminary validation. And even though our demo app is only targeted for GPUs, we adapted the kernel slightly so that we could run the same algorithm, or an adapted CPU optimized algorithm on the CPU. And for comparison, we just looked at the axial energy deposition. So even though the kernel itself is only about 2 pages of code, there's a lot of other, with the encapsulation that we're using, there's a lot of actual work going on in each one of these lines of code there. So there's actually quite a bit of code being touched, but it's relatively simple to have this one kernel, and that sort of exemplifies the modularity that we're going for. Do interaction length sampling, we move the tracks around, we do the actual full Compton scattering kernel, construct secondary particles and allocate them on device. We allocate hits on device and assign the energy deposition to them. And we have a couple of helper kernels that do tallying, basically. So preliminary results, we found good agreement with JANT4 physics, and the CPU and GPU Celeritas versions gave us identical results. A little bit of performance analysis. We ended up doing quite a bit more, but we don't have time to go into it in detail. But we found that basically our performance on this particular mini app saturated at about 1 million tracks running simultaneously on the device. And the total overall speed up, including the overhead for the multiple kernel launches, was about a factor of 150 for a single thread on our NVIDIA Tesla V100. And so we think this is probably going to be a relative upper bound for raw performance. There are going to be bits and pieces that could make us better in some ways compared to the CPU, and there's going to be a lot that could hurt us. But we think that this is a good starting number to have. Okay, summary and future work. So we've done quite a bit so far. We've got our infrastructure all set up with having the code base, procedures, and project tracking on GitHub. We've got a build system that supports unit testing. We've got continuous integration underway to make sure that our code is stable and robust. We've integrated VekGeom and have some example apps that I showed. For the physics, we've got a framework in place that'll allow us, or that is allowing us really, to develop the multiple physics kernels in parallel so that we can, that the different people working on the project can all contribute meaningfully to the physics. We've pulled in the ability to generate particles from HepMC3. We've got our working and highly performant on-device allocators for generating secondary particles and hits. We've got our interaction kernel that I showed earlier, and then we've got the framework in place, as I mentioned, to get more EM physics models up and running quickly. Oh yeah, and this is all since basically about June is when our first code commit was. So for the next couple of months, we're going to be continuing our work on the standard EM physics models, including pulling over the data from cross sections, implementing materials, and supporting tracking through multiple materials in a single model. We are going to be pulling the physics and geometry together into a transport loop, as well as supporting multiple processes at the same time. So we've got some ideas for how this will work, especially based on the background that we have in Shift, where we have parallel parallel work being done. So we think that we have a good background for getting this up and running and integrated. And then finally, doing the EM field integration and propagation. So yeah, our 1 year milestone that we kind of like to have is a fully representative standard EM physics list with constant uniform electromagnetic field that we're moving through, integration with VekGeom so that we can actually do all of the transportation on the device and be able to export hits from the GPU and save them to the CPU and thence to the disk. So at that point, we'll be in a really good place to do detailed performance analysis to see what our bottlenecks could be and how we can overcome those, as well as establish a baseline figure of merit for our simulation performance. And of course, to identify the upcoming risks to performance and robustness and how we can mitigate those. That's all I have. Thank you.
All right, thank you, Seth. Let's see.
There is a question from Ben.
Well, not a question, just a comment. To say this idea of having an application that demonstrates offload using the tasking framework would be another good area for us to collaborate on across all three projects. And I think also as a depending on how much of Celeritas or Adept or others it uses, it will be a good thing to port back into JALT4 as well as an exemplar of doing that.
Yep.
I don't see any raised hand, but you have a question, Jonathan.
Yes, Seth, you mentioned you've been copying tracks back and forth. Right now, you said the requirement was for things to be initialized on the CPU and copied over. Have you looked into using the UVM?
No, so right now the only copying that takes place is from so our plan once we finish once the VekGeom initialization starts working robustly on the GPU, we only want to copy over the basically the primary particles that are coming out of the event generator, and that'll just be a once only copy. We don't think that we'll need to use too much back and forth. We'd like to keep everything on the device except on the very front end and back end, and do that asynchronously. So there's a couple of reasons include, yep.
Well, so I mean, what about once you get the hit scoring? Yeah,
so I think that'll just be an asynchronous host to or device to host transfer. The UVM, its benefit is that it saves the programmer effort in figuring out what needs to go where. But I think the way that we've got it sketched out should allow us to, without a lot of hassle, sort of schedule effectively when those transfers need to take place. Does that make sense?
Yeah, I just in terms of prototyping and getting some of these things.
Hey, Jonathan,
have a lot of work.
Sorry, hey, Jonathan, just a quick question. Have you done any kind of performance looking at? I mean, there's a lot of different. I know in ECP we have a lot of different performance numbers that float around about UVM usage, and a lot of it depends on whether you're touching data in between kernel launches, which necessitates, paging back and forth, whether you're running out of memory on device and it necessitates paging, and just general performance. The other reason we like to manage memory ourselves is that newer architectures, different, I know we're speaking heavily NVIDIA based here, but the support for it on other GPUs, particularly AMD, is pretty poor. Do you have any performance numbers in the back of your head that makes you think UVM is going to give you reasonable, or are you just talking about it for convenience?
Just early on convenience, getting things working. I know
that totally makes sense, by the way, but yeah, we've kind of already built all this stuff in, so we'd rather just do it, but I agree with what you're saying in general.
Okay, we have a question from Marilena.
Yeah, thanks. Hi, Seth. I have a question about your mini app. So on slide 12 and 13. First, just to understand myself a bit better, are you actually using any transport in this simulation? So Are you using any geometry, and or is just a stepping loop which is implemented? This was not very clear to me. And second, do I understand correctly in this plot where you are comparing Geant4 and Celeritas results? I mean that there is this percentage difference which is sometimes greater than 10%. So do you understand why there is this difference, if this is related somehow to, I don't know, random numbers or non-reproducibility of your simulation, or you have other explanation for that?
Yeah, those are great questions. So first of all, with a stepping kernel, even though, so we're tracking the physical positions of the particles. So we are actually, keeping track of a position and direction for every track. But because it's effectively a uniform infinite medium, and so there's no geometry interaction itself in this demo app. But that's on the line for the next one that we're planning on putting out in the next couple of months. So no VekGeom.
You're only invoking the physics process, right?
Say again?
So you are only invoking the KleinAshina process every time, just no geometry involved at all.
There's a geometric tracking taking place, but they're never going to hit another surface. So there's no surface crossings. And so it is like simpler, like you're saying. But it's not just a single point that's repeatedly trying to emit particles. It's actually, keeping track of the position, sampling the new direction, sampling the direction of the secondary, that sort of thing. That's kind of what I'm trying to get across. For the Geant4 comparison, so this is a differential result. So these are very finely binned along the z-axis. So the coarseness of the error is highly affected by the statistics. If we move to have coarser bins, that relative error would decrease. We're also only able to run a few thousand tracks on Geant because of the memory requirements for the output on disk. For our comparison Geant demo app was fairly rapidly set up. So it outputs basically the MC truth output. So I think at 64,000 particles or something like that, we were getting many gigabytes of data on our little laptop. So there are better ways that we could compare this and do better validation, but this is basically just statistical noise. And since we're not reproducing the Geant4 random number stream, and that there's going to be some implementation differences from Geant4, we're never going to expect numerically identical results.
I see. Thank you.
So there is one last question by Andre.
Yes.
That you were mentioning for this mini app, you were mentioning a speed up of something like in the order of 100. And you were saying that this is the high expectation value for what you hope. So do you think that after adding extra complexity like geometry, stopping at boundaries, more physics processes, is it this number, reasonable expectation, or it's going to be much lower than that?
I would, my back of the envelope guess is that it's going to be about a factor of 2 slower at the end of the day once we get all of the features and capability in place. But I think that there's a lot of opportunity in how we do this, and I think that the abstractions that we have in place and the framework that we've got have give us a good way forward to playing around and seeing how we can bring that number back up again.
Hey, Seth, I can add too, for shift production runs, I don't want to it's not apples to apples. We see about a factor of 160 in real production problems, but you have to acknowledge that our geometric amount of time we spend in geometric queries is probably going to be quite a bit smaller than what we spend in this type of application, A, and B, we just don't have as many processes per event. We only have neutrons, basically, or neutron photons. So it's a much simpler process loop but this is on the order of what we see in production stuff and shifts. So there is some reasonable expectation. We won't, you know, lose an order of magnitude, but somewhere probably between, as Seth said, a factor of 2 and where we're at now is probably reasonable to think.
Okay. Looks like we don't have any more